Hi, everybody. And so no formal lecture this week. I'm just going to give a bit of an overview of the unit and the most important sort of key concepts for your test coming up on Friday. So we started off in this unit discussing stoichiometry, which is looking at the relationships involving the amounts of things in chemical reactions. And we referenced this slide quite a bit in this graphic because this really is your roadmap for all of these types of problems. And so in all of these types of problems, you are going to be given the amount of something, of some sort of chemical or species in the reaction, and you'll be looking for the amount of something else in the reaction. Maybe you're given one of the reactants and you need to find the amount of one of the products. Maybe you're given the amount of one of the reactants and you need to find out how much of another reactant, or you're given a product and need to find how much reactant you started with. Doesn't matter what two things you're comparing. You can use this roadmap to compare any two things in a chemical reaction. The key thing to note is that remember that this is all centered around the number of moles. And so whatever you're given for an amount of whatever it is that you're starting with, you need to find a way to convert that given amount to moles. And so if you're given the mass of that substance, you use the molar mass to convert that to moles. If you're given the number of particles, you use Avogadro's number. If you're given the volume of a solution, of an aqueous solution, you would use the molarity. You could even be given the volume of some sort of solid, and you could then use the density to get that to mass, and then the mass to moles using the molar mass. But then we use however we have to get there. We get to moles of whatever it is the substance is that we're starting with, and then we use our stoichiometric ratio from our balanced equation to get to moles of whatever it is that we're looking for. And then from there, we can use all the other tools that we've learned to get to whatever the final amount is that we're being asked for in the question. And so this key. This roadmap is key for us in that remember that this is our bridge, our stoichiometric ratio is our bridge between the two things in the chemical reaction, but we have to be comparing moles. And so we have to get to moles somehow, and then convert to moles of the other thing, and then to whatever it is that we're looking for an amount on the final answer. And this is just sort of more of that, just again reiterating that we can't go directly between amounts. We can't go directly grams to grams, but we would always be going through moles. And so moles is our main counting unit, which means when in doubt, mole it out. If you're having some difficulty with some of these questions and you're not sure where to begin, you're not sure what to do for your first step, then take a good look at what you're given for information and try to convert it into moles. Do whatever you might have to do to convert that into moles and go from there. And then when you're using your stoichiometric ratio from your balanced chemical equation, remember that's just a conversion factor. And so in this example here, for instance, so we have I2 plus F2 to make IF3, to make iodine trifluoride. We always have to make sure the equation is balanced. And so you always want to double check that. Some of the problems that you have on the exam will be balanced. Some might not be. So you may have to balance the equation first. So definitely take a look for that. But in our final balanced equation, we have 1 mole of I2 plus 3 moles of F2 to give us 2 moles of IF3. That then provides us with stoichiometric ratios between any two things in this reaction. We have 1 mole of I2 to 3 moles of F2, 1 mole of I2 to 2 moles of IF3, 3 moles of F2 to 2 moles of IF3. And then we can express that stoichiometric ratio, just like in any conversion factor, we can express that ratio however we need to in order for everything to cancel out the way that things need to cancel out. And so for the first one, we can either think of this as 1 mole of I2 to every 3 moles of F2, or 3 moles of F2 to 1 mole of I2, and so forth. And so then just, again, to show this again, so we were just talking about with that, our stoichiometric ratio, we're talking about this step right here, converting of moles of one substance to moles of the other. And then we've got the rest of the roadmap to do whatever other conversions that we need to do. Sometimes we're given amounts of 2 or more of the reactants. In those cases, there's always going to be an insufficient amount of one of the reactants to consume the others completely. In other words, one of the reactants in a reaction will always limit how much of the product we can actually make. We use the cooking analogy here quite a bit. There's always going to be, if you want to make an unlimited number of chocolate chip cookies, there's always going to be one thing in particular that limits the actual number that you can make. Maybe you only bought 1 bag of chocolate chips, and so there you go. That's going to limit you to probably a couple dozen cookies, depending on how large you make them. But and it's the same thing in a chemical reaction. One of the reactants will always, always, always limit the amount of product that you can actually make. And so that reactant is referred to as the limiting reactant. And we talked about several ways to go about limiting reactant problems. You can either compare the mole ratios of the reactants, and so you take what you convert your given amounts to moles, and then divide that ratio down. So you have one of them gets divided. Basically, you divide one by the other. Remember, and so you get the amount of that reactant per one of the other one, and then do the same comparison to your stoichiometric ratio. And so say, for instance, in our iodine and fluoride example earlier, if we convert our given amounts to moles, we'll just come back to this. So if we convert our given amounts to moles, whatever we started with, and then let's say that we found out that we have 2 moles of F2, what we have is 2 moles of F2 to every 1 mole of I2. We would then compare that to the ratio of what we need, which is 3 moles of F2 to 1 mole of I2 from our given balanced equation. And so then we would say that, okay, that F2 is our limiting reactant in that reaction. Or the opposite way, let's say we do this out and we see that we've got 5 moles of F2 to every 1 mole of I2 from our given amounts. Then we would say, well, that 5 is more than what we need for fluorine. Therefore, the iodine is actually limiting us in that reaction. And so we can compare those ratios of what we have compared to what we actually need. Another way we talked about is just flat out doing out the whole problem. Just take one of the reactants, do out your stoichiometry problem as normal based on that reactant, and then do it out again completely based on the other reactant. Whichever one produces least, that is your actual limiting reactant, and that amount of product will be how much you make. Finally, we also looked at the use of before, change, and after tables. And those can be very useful, especially in situations where you need to find the amounts of all products at the end of the reaction, all products, and even then how much you can use these to find out how much of the excess reactant remains. So if you need to find that level of information, these before, change, and after tables can be very useful. But any of these methods will work. Whichever one you have found to be the most effective for you in determining limiting reactant problems, that's what you should do. So you should hopefully be doing enough practice before the exam, if you haven't already, to figure out which method you are most comfortable with, and which one you are fastest and most efficient with using. We also have what we call our percent yield. So remember, when we do out a stoichiometry problem, what we are actually calculating there is the theoretical yield. And so in other words, if everything goes fine, if everything goes perfect 100%, and I recover all of the product that I should make, that's how much we should actually make. And so when you do out a stoichiometry problem, you're calculating how much you should theoretically get if everything goes perfectly. Everything doesn't go perfectly. This is in a real life lab situation. And so the actual yield would be how much you actually got from performing the experiment. And so it's useful to calculate that as a percentage. How much did we actually get divided by how much we theoretically would calculated we should get from our stoichiometry problem, and then just times 100 to convert that to a percent. And that gives us the percent yield of our reaction. We looked at a few different types of chemical analysis, and so ways that we can use stoichiometric principles to analyze various samples of compounds. In this example of a gravimetric analysis, we had a mineral sample of thernodite. We had 0.123 grams of thernodite in this example. And what we did here is what we wanted to find was the percent of that thernodite that was made up of sodium sulfate. And so we dissolved it. And so the sodium sulfate that was in the mineral went into an aqueous solution. We reacted that with some aqueous barium chloride. And then our solubility rules tell us that we're going to get some solid barium sulfate from that. And so in this gravimetric analysis, we then filter out that solid barium sulfate. And here we found that we had 0.177 grams of the barium sulfate. Now, the key with this type of analysis, the key with a gravimetric analysis problem, is recognizing that the only source of sulfate, the only way this barium sulfate could have formed is from the sodium sulfate that was initially present. And so we can do a stoichiometry problem to work it through and say that, well, if I got 0.177 grams of my barium sulfate, we work it through just like any stoichiometry problem. And we see that in our initial sample, there had to have been 0.108 grams of the sodium sulfate. We take that 0.108, divide it by the 0.123 grams of the entire mineral that we had initially. And again, multiply by 100 to convert to a percent, and we come up with our percent composition of sodium sulfate in this original mineral sample. Another main type of analysis we looked at was combustion analysis. And so I don't actually have an example worked out here. There are lots of examples that are on the website for you and lots that were worked out in lecture and in the supplemental video. But remember, in a combustion analysis, what we can do is take a generic hydrocarbon, something that's made up, for instance, of just carbon, hydrogen, and oxygen. We can combust that, burn it with oxygen, and collect the H2O and the CO2 that are produced. Based on those amounts of H2O and CO2, we can then go back and figure out how much of the original sample had to have been carbon, how much had to have been hydrogen, and how much had to have been oxygen. And using that can then lead us to finding the empirical formula of a compound. If we also know the molar mass of the compound, we can use that information to find the actual molecular formula of the whole thing. Pretty powerful type of analysis. We also talked about using molarity as an amount. And so remember that most of our reactions take place in an aqueous solution. And so it's useful for us to have a way to calculate how much of the compound that we're interested in is actually in a certain volume of the solution. And so we use molarity for that. Remember, molarity is the moles of our solute divided by the volume of the solution. And we denote it with a capital M. And so 0.2 big M, 0.2 molar, means that we have 0.2 moles of the compound per every liter of solution. And that just gave us another tool in this arsenal of being able to calculate moles and go back and forth. And that was, in fact, what we would use if we're following this pathway right here. We would use the volume of an aqueous solution and the molarity in order to get to the number of moles. We talked about the dilution equation. And so if we have, for instance, a very concentrated solution, and we want to know how much of that solution that we would need in order to make a certain volume of a lesser concentrated solution, we would use our dilution equation to find that. M1V1 equals M2V2. We talked about how to use this. We looked briefly at pH and pOH. And so these were our key equations that we need for looking at pH and pOH, where pH is going to equal a negative log of, and remember we talked about H3O plus or H plus being basically synonymous with each other. But pH is the negative log of our hydrogen ion concentration. pOH is the negative log of the OH minus concentration. And pH and pOH are related to each other in that the sum of those two in any solution will always equal 14. So these are definitely some useful equations that you'll want to know. With acids and bases, we also talked about one other type of chemical analysis known as a titration. In the titration, we take the volume of one compound, convert that to moles of that compound, use our stoichiometric ratio to convert to moles of the other compound, and then finally, we could go to a volume of compound 2. So the same, just backtrack a little bit here quickly, but a titration essentially just means that we're going directly across in our big pathway. And that's just another type of analysis that is helpful for us. Then we switched our conversation over to energy. And so remember that when we're looking at the energy of any system, we are always looking at the energy from the perspective of the system. And energy is always conserved, but can definitely transfer back and forth between the system and the surroundings. If energy is being absorbed by the reaction, so energy is flowing from the surroundings into the reaction, that we call that an endothermic reaction. Energy is coming in, versus a reaction in which energy is given off. In that case, energy is flowing from the system to the surroundings, and we call that an exothermic reaction. Let's say we're running these reactions in water. We might be able to actually feel an endothermic reaction get colder, because remember what we're actually feeling, the water is the surroundings. So energy would be flowing from these surroundings into the reaction. And so what we're feeling is the effect in that case of what's happening to the surroundings. The surroundings get colder because they lose energy to the system. In an exothermic reaction, if we're actually holding on to that and running it in a beaker, we would feel the water get warmer because the reaction is giving off energy that then comes to the surroundings, and so we would feel the water heat up. We talked a fair bit about specific heat capacity being the quantity of heat that is required to raise the temperature of 1 gram of substance by 1 degree. And we talked about using the specific heat capacity, which is denoted with a lowercase c, in our classic energy equation, Q equals mc delta T, where Q is equal to the amount of energy gained or lost as heat, usually in joules, but might be kilojoules, depending on the situation. Make sure you're watching your units. M is our given mass of a substance, typically always in grams. Delta T is our change in temperature, and C is our specific heat. Now remember here that the sign is very important of Q, because that tells us endothermic or exothermic. A positive Q is an endothermic reaction. Negative Q is an exothermic reaction. The way to ensure that you're getting the proper sign with a Q equals mc delta T problem is making sure that you're setting up your delta T correctly. Always, always, always final minus initial. So you absolutely might be getting negative delta T's, and that's fine. That would end up leading you to a negative Q, which would indicate an exothermic reaction. We talked about heat transfer in cases like this, where we might heat up a piece of metal, drop that into water. Those are eventually going to come to a thermal equilibrium in which they'll both be the same temperature. And we talked about how we could actually use that relationship in a case like this here. And so I would encourage you to try this problem again if you want, but we can actually use that to find the specific heat capacity of an unknown metal, because we can set those Q equals mc delta T expressions equal to each other. And so in this case here, the metal, when we drop it down into water, is going to lose heat. And that's going to have its own associated Q equals mc delta T. The water is going to gain heat. And so the water will have its own Q equals mc delta T. We know the mass of the water in this example here. We can measure the temperature change of the water. We know C of water. And so using that information, we can calculate the heat gained by the water. Law of conservation of energy tells us that has to be exactly equal and opposite to the heat lost by the metal. So we can set that to equal our Q for the metal. We would know M and we would know the delta T. So we can use that to algebraically solve for C. Now it's a lot just to hear it like that. So again, I would encourage you to look back over this problem when we worked it out and several others like this that we have worked out as examples. But it all comes down to that law of conservation of energy, where the heat lost by the metal as it cools down must be equal and opposite to the heat gained by the water as it warms up. We also looked at the energy changes associated with changes of state. And that in this example, if we have a sample of solid ice at -50, in order to get that to a gas at +200, we first have to warm the ice up until it gets to the melting point. At that point, all the energy goes into melting the ice from 100% solid here to 100% liquid here. Once it's all liquid, the energy can now go into warming it up again until we get to the temperature of the boiling point. Now all the energy goes into transforming this from 100% liquid here to 100% gas here. Now the energy can go into warming it up again. And so to actually calculate each of those individual steps, we would use Q equals MC delta T. For any phase where we're actually warming up, we would use Q equals MC delta T. For the phase where we're actually melting the ice, we use the delta H of fusion. And so Q would just equal our mass times the delta H of fusion. Remember, no delta T there because the temperature doesn't change. As you're melting or as you're boiling, the temperature stays constant. Another Q equals MC delta T as we're now heating our liquid water. To calculate the heat associated with boiling, we're going to have our mass times our delta H of vaporization. And then finally, another Q equals MC delta T in heating the steam. And just remembering that C is different for solids, liquids, and gases. And on the exam, I do provide you with that information when you do need it. I tell you what C's are, what the various C's are if you need those, and I give you the heat of fusion and heat of vaporization. You don't need to put those on your cheat sheet. We looked at thermochemical equations, where the heat involved in a reaction is now given as part of the information about the chemical reaction. And so in this case, 1 mole of carbon plus 1 mole of O2 to form CO2 is an exothermic process which releases 393.5 kilojoules of heat. If we reverse that, CO2 now decomposing to carbon plus oxygen, that's going to reverse the sign of delta H. Now, another key component is that this heat is the amount of heat involved with 1 mole of carbon and 1 mole of O2 and 1 mole of CO2. If the coefficients were different here, then that would be the same thing. If we had, for whatever reason, maybe we have 2 moles of C here, then the heat provided is taking that 2 moles into account. And so if you change it, as we'll see in a second with Hess's law, but if you want to know the amount of heat involved with 2 moles of carbon plus 2 moles of O2 to make 2 moles of CO2, then you would need to double the amount of heat involved. This heat is particularly tied to the stoichiometry in this particular equation. And so whatever you do to the equation, you have to do to the heat as well. There are different ways that we can go about finding thermochemical data. We talked about the use of calorimetry. We talked about finding the data indirectly through Hess's law. And we also talked about using heats of formation for the products and reactants. Remember, in calorimetry, what we essentially do is we run a reaction in water, and we can measure the effect on that water. We can measure the Q of the water by knowing the mass of the water, the delta T of the water, and we know C of water. So if we run a reaction, we can measure the Q, the heat involved that the water either gains or loses, which will be equal and opposite to the amount of heat that the reaction either gains or loses. And so we can compare those two using our law of conservation of energy. And That does not, however, work well for reactions that can't be either controlled or directly measured. So we also talked about using Hess's law, in which we're going to combine different reactions in order to get to our target reaction. And so in this example here that we looked at, we want to know the information involved with the decomposition of zinc carbonate. We can't measure this reaction directly though, but we do have information for these three reactions. And so what we have to do in Hess's law problems is find out how to manipulate these equations so that the things that we don't need cancel each other out. They would cancel each other out by having the same number on the reactant and on the product side. But we also have to manipulate these equations so that what we want for reactants are on the reactant side and what we want for products are on the product side. And so with this problem here, one of the things that we first see is that our zinc oxide that we want as a product is actually a reactant in our given equations. And so we're going to reverse that equation. We reverse that equation, and we also have to reverse the enthalpy like we've talked about. We also see that the zinc carbonate we need as a reactant is actually a product in our given equations. So same thing, we're going to reverse that equation, and so we reverse the enthalpy. It now looks like we have all of our products and reactants where we want them. So now we have to look to see, does everything cancel out the way we need it to, and are we left with only the things that we want? And we can see that indeed, everything extra cancels out here, both on the reactant and the product side. We have one H2CO3 as a reactant. We have one H2CO3 as a product. We have an H2O, a water here as, so yeah, one water here as a product, another water here as a product. So two waters as products and two as reactants. So that goes away. And our zinc hydroxide. And that means that we are just left with the reactants we're looking for. So that tells us that we've manipulated our equations in the way that we need to. So now we know we can finally just add up the enthalpies and we'll come up with the answer. The other way we talked about coming up with thermochemical data is through the use of heats of formation. And so when we're finding the heats of formation, the heat of formation of something is the amount of heat that's required to form 1 mole of a compound from its elements. The heat of the heat of formation of an element, remember, is 0. And we talked about the way to go about these problems is you would have a table of heats of formation. A very typical example might be find the heat associated with this reaction. And so you would use your table and add up all of the heats of formation of the products, multiplying them by their stoichiometric amounts in the reaction. If you have 6 moles of something in the reaction, you have to take that 6 and multiply that by the heat of formation of that element. So remember that key part. But you take the entire sum of the heats of formation of the products minus the entire sum of the heats of formation of the reactants. And that would give you the final heat of formation of the whole entire reaction. And so that's just a brief recap of everything that we talked about in this unit. Very brief because we talked about a lot of things. This was a very heavy, very dense unit. You have lots of material to help you prepare. And so let's just look through some of that again real quick. So remember, on the website, if you go to the Unit 2 materials page, you've got, first of all the different lecture slides. So our stoichiometry lecture here and our thermochemistry lecture here. Those are the slides that I use as a backdrop to my lectures. So you might find those helpful. There's a whole slew of supplemental videos. So these just break things down into smaller chunks. Maybe you're finding that you really need some more help with just Hess's law. There's a Hess's law video here, or just some of those phase changes, some limiting reactant information. And so these break it down into smaller chunks for you. A couple of various handouts that you might find helpful, and then just a whole lot of extra practice here as well. All of these will have answer keys in some way. So the keys are possibly built right into them. Like in this practice worksheet here, you've got some specific heat problems, and then you have the answers right there to check yourself. Or in some cases, If the key isn't built in, I've made an answer key for you. So you'll have answer keys to all of these different practice problems here. Remember, Chem 101 also has a lot of different practice problems that I've made available to you. If you go here to Unit 2 Practice, we can see these again broken down into various categories. If you want to look at just some general stoichiometry help, yes, there's some help here, some limiting reactants, and so forth. Hess's law and heats of formation. So these all provide directed practice for anything more that you think you might need, with the typical help that you do find from Chem 101, and assistance with various comments if you get the answer wrong. And with these, there's no limit. Like in homework, you've got your 5 attempts and that's it. There's no limit to these practice problems. You can just keep on trying until you finally get the answer right. Practice, 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 practice. I cannot stress that enough, that is the way to prepare for this exam. Do as many problems as you can get your hands on. That is what is going to get you to a point where you can sit down for the exam on Friday and be able to just do the questions. Remember, like I said in the email, that these exams are set up and arranged so that somebody who truly has mastered this material, somebody that truly knows how to do all of these problems, can simply sit down and do them without thinking about it. And in those cases, those people will have enough time to complete the exam. If you're struggling with how to do things, if you're sitting there thinking, oh, I really don't remember how to do this, maybe I'll try this and see if it works. If you're doing that for too many of the problems, then you are going to be crunched for time and you won't have time to finish the exam. That's not just a function of this online exam. That's how exams are designed in general. And so the way that you get around that is to really master the material, to really learn it. And so spend time doing as many problems as you can. That is going to take time. Remember the exam, the allowable materials. There's not much that you actually, quote, need for this exam. And so, where's my, there it is, exam info page. And so exam 2, really the only big materials that I've made available for you are our standard periodic table, always allowed a periodic table. You're definitely allowed to use a scientific calculator. And it's not listed on here, but it will be. You are also allowed one standard sheet of paper, cheat sheet. Write handwritten, write whatever you want on it. Just be efficient in what you write on that. Remember, if you're using that to rely on things, what am I trying to say here? If you're using that to rely on too much, you won't have time to use it. So keep that in mind as well. And so lots of study tools available for you. Email me. There are still lots of LA sessions this week. The LA sessions are all focused on exam prep. Help each other on Brightspace. Do whatever you have to do to prepare for this exam. And so, and then actually I will be right back with somebody else who just wants to wish everybody well on this upcoming test. And here he is. Henry here just wanted to say that he knows everybody can do it. He has faith in you. He thinks that if everybody studies hard and does as many problems as they can, that they can do very well on this exam and make themselves proud. Don't you? Do you think that? Do you think that? Can you give everyone a smile? He doesn't make it down to my office, I mean to the beach that often, so he's looking all around. Nice palm tree right behind you, isn't it, buddy? Yeah. And so breathe. This will be a hard test, but I have faith in you too. You all can do it. You're all perfectly capable. It's just going to require a lot of work in order to get ready for it, in order to really prepare. But both Henry and I here have a lot of faith in everyone, and we know that you can do it. And so, as always, I'm here for you. Email me with any questions. Use each other to help on Brightspace. And then breathe a sigh of relief on Friday after you complete it. The test will be available to you from essentially midnight to midnight on Friday. Remember also that as per the syllabus policy, there are no alternate dates. If you do miss the exam for whatever reason, I will average your 2 other exams, subtract 10, and that score would replace your missed exam. And so that the Friday is the only possible day to take this test, coming up on Friday, March 26th. And it will be available from 12:01 a.m. to 11:59 p.m. on that day. And so good luck to everybody. Henry says bye-bye. We're going to go back to the beach and we're going to soak in the rays, aren't we, buddy? Yeah. All right. Email me with questions and good luck to everybody.